Chapter 5, Lesson 5. Sorry I can't be there today, especially for this lesson. It's a bit of a intense lesson. There's only 2 examples. However, what we're doing is we are putting everything together so far that we've learned this chapter and stuff that we've learned in the past. So as you can see, we are going to be doing curve sketching. So we are going to actually sketch a graph. And we are going to use these 8 steps that you see lined out here to sketch the graph. So first thing we're going to do is we're going to state the domain, right? We're going to take a look at the expression I give you, the function I give you, and we're going to predict what the domain would be. Then we're going to figure out our x and y intercepts, which is not new to us. And then we are going to figure out the symmetry of the graph. Is it a vertical reflection? Is it reflecting horizontally? Is it maybe reflecting vertically and horizontally? So this is actually something you haven't seen quite before. And so this stuff that's written right here, the even odd stuff, I'm going to explain that as we actually get to that example. It'll make more sense if I just show you. Number 4, we're going to state if there's any asymptotes. Usually if there's a denominator, there's an asymptote, right? Then we're going to get into the stuff that we've learned so far this chapter. We are going to state the intervals of increase and decrease, right? So where is the graph going up? Where is the graph going down? Then we're going to determine where our local max and mins, right? Our highs and our lows. Then we're going to figure out our concavity. When are we concave up? When are we concave down? And the inflection points. And just a reminder, the inflection point is defined as where a graph switches from concave up to concave down or vice versa. And then once we have all of that information, we're going to finally sketch the graph. So you can see here that you have the entire page to fill in all of these steps. So you have a lot of room to write and draw the graph at the end, but just be cognizant of your space. Please keep this nice and neat and try to write generally small-ish just to make sure you don't run out of space. Okay. So I'm literally just going to go step by step here. So the first thing I said we're going to look into is the domain. So this is a polynomial function, 3x to the 5 minus 5x cubed. Pre-Calc 30, we learned all about those. Polynomial functions always have a domain of x is an element of real numbers. So we know our graph, whoops, why am I not doing squigglies? We know our graph is going to go all the way left or all the way right. Okay. All right. Step number 2 are our intercepts. I'm going to go over here to do that. So I will start with my x-intercepts first. We know by now that to do x-intercepts, we set y equal to 0. So I have 0 equals 3x to the power of 5 minus 5x cubed. All right, so the only way I can really factor this at this point is to remove the GCF, and the GCF here is just x cubed. When I divide out x cubed, I get 3x squared, and then I still have that minus 5, but the x cubed minus x cubed is x to the 0. I have no x's left. Okay, so now that I have those factors, I take that monomial that's automatically going to be set equal to 0, so x is just 0. And here, when I set this guy equal to 0, I'm going to move the 5 over. I'm going to divide each side by 3. And then I am going to finish off by square rooting each side. Don't forget the plus or minus whenever we square root. And because we are graphing, we can use decimals here, okay? So you take your calculator, you go 5 divided by 3, and then square root that answer, and you should get an answer of about 1.29. Okay. Now beside that, I'm going to do my y-intercept. And to do that, I set x equal to 0. And so remember that with polynomial functions, the y-intercept is always your constant. So it's your c value at the end. I don't have a constant, obviously it's 0. You could go through the motions and you could plug 0 in for each x, because that's really what the y-intercept is, right? Y when x is 0, but you can clearly see it's always just going to be the constant because both those terms will just disappear. So there you go. I have a few x-intercepts here and I have a y-intercept as well. All right, step 3. I'll go right underneath there. So step 3 is the symmetry. So this is new to you. So you can see up here in the symmetry, I have to take my f of x and I have to figure out if it's equal to f of minus x, or I take negative f of x and see if that's equal to negative x, which that's really messy and complicated. So here's the easy way of how you're going to do it every single time. And this is how I want you to do it every single time. We can see in both options, we need to figure out f at negative x, right? So we're going to figure that out first. No matter what, start by figuring out what is the function when x is negative, okay? So I take f at negative x. So all that means is wherever I see an x, I replace it with negative x. And now I just simplify and see what happens. So if I have a negative x to the power of 5, it will remain negative, right? So this whole term will end up being negative 3x to the 5. Then if I take a negative x and I cube it, if I cube a negative, it remains negative. So the result of this, just like the other one, is negative. And then when it matches up with that guy or pairs up with that negative already in front of the 5, it would actually end up being positive x cubed. So this is the result we get. And we have to now compare it to my original. So if we look at my original, you can see here that originally I had a positive 3 and then a negative 5, right? My new one, it's flipped. I have a negative 3 and a positive 5. So all my symbols have flipped, which means this has become the opposite of f of x, right? It's become the opposite. Every symbol has flipped. So if we go back up to our two options, up here, I'm just going to erase this. When we go back up to our two options, we have this option, okay? So we plugged in a negative x in my f of x, and the result was the entire function got flipped. So all the symbols changed. So that means we're odd. And for the next example, I'm going to show you of an example where it's even. So you'll see the difference between the two, okay? But just always start by finding the negative x and see what happens. Does your original function stay? Does it stay the same as the original, or does it become the opposite? So because we have become the opposite, we know that the symmetry here is odd, okay? When we have odd symmetry, that means that we are going to be symmetric about or around the origin. And the origin is 0, 0, obviously, right? So we are symmetric about the origin, which means we are symmetrical in terms of x and y, which means we will be symmetrical vertically and horizontally, okay? And when we're sketching it, I'll refer back to that so you know what I mean. But the graph will have symmetry, is what that's saying. Okay, step number 4, I will do over here. Okay, so step number 4 is to state our asymptotes. We have no asymptotes because we have no denominators. Easy peasy. Moving on. Step 5. Step 5 is where we're going to get into the stuff that we've been learning this chapter. So the first thing is I want us to find the intervals of increase and decrease. One is our graph going up and one is the graph going down. So we did this in lesson 1. And in lesson 1, we learned to figure out when we are increasing and decreasing is to first find the derivative, the first derivative. So I go back to my original function. I find the derivative of 3x to the 5, which would be 15x to the power of 4. And then 5x to the 3 becomes negative 15x squared. Okay, so there's my first derivative. And still going back to lesson 1, the next thing we did is we found the critical numbers. So to do that, we set that equal to 0 and we factor the right side if possible. I see that I have a GCF of 15 and x squared. I can take all of that out. When I divide my first term by 15x squared, I am left with only x squared left. Negative 15 divided by 15 is going to be a negative 1 because the x squareds also eliminate. So you're left with just a negative 1. Okay, once you factor, as always, you set each guy equal to 0. So this monomial out front will always result in an answer of 0. And then we are going to factor this, or you could factor it as a difference of squares, or you could solve, send the 1 over, and square root each side as long as you remember to put the plus or the minus, okay? Factoring it is the safe bet because it'll always give you both answers. So if you're opting out of factoring and choosing just to solve this way, you need to remember the plus or minus. So we have 3 critical numbers, okay? Once we found our critical numbers, this is again back to lesson 1. Once we found our critical numbers, we did sign analysis. Now, sign analysis, you can either do that table of values and plug numbers in to see the symbols, or you can try to visualize the graph. We can visualize this. Okay, this is what I'm sketching. We can visualize that. That is a polynomial function, degree 4, and it's positive. My leading coefficient is positive. So I know both of my arrows will be pointing up. I know that. I know that I have a -1, a 0, and a 1 as my critical numbers. And now, here's the one thing that you may have forgotten is this guy right there. So this whole factor right here, this 15x squared, my GCF, it equals 0. Like the result it gives me is x equals 0. Okay, fine. But because of that exponent of 2, that means that this factor right here has a multiplicity of 2, and that's a pre-calc 30 term. So in pre-calc 30, we learned about multiplicity, which is essentially the exponent on the factor. Okay, so that has an exponent of 2. An exponent of 2 has specific behavior. What that means is when we approach this critical number on my graph, we don't actually cross at 0, we bounce back like a parabola would. So what I mean by that is we will come down through -1. -1 has a multiplicity of 1. If you go look up here, it has a multiplicity of 1. There's only one of those guys, so we go right through. But then when I approach 0, I don't go through again. It has a multiplicity of 2, so I bounce back down. Then I approach 1, and again, x plus 1, or these both have a multiplicity of 1. And so I bounce back up. Okay, so that is my sign analysis. So I know I am positive, positive, negative, negative, positive, right? So once we have that down, we can figure out our intervals of increase and decrease. So my intervals where I'm increasing is wherever I'm positive. So I am positive from -infinity to -1 with a union. And then I'm also positive from 1 to infinity. And decreasing, I am decreasing from -1 to 0, union 0 to 1. You don't just say -1 to 1. I understand we are negative this whole stretch, but technically at that point right there, I am neither negative nor positive. 0 has no symbol attached to it, so it cannot be included in your decreasing intervals. So you have to actually block it. -1 to 0 and 0 to 1 is when you are negative. So there's your intervals of increase and decrease. That's all of number 5. Moving on to step number 2, or sorry, step number 6. All right, step number 6 is your max and your mins. So again, back in lesson 2, I believe it was, is when we did max and mins. And I've actually taught you a couple of ways to find max and mins with the first derivative test and the second derivative test. Because I have all of this work here with the first derivative already done, I'm going to use the first derivative test because I've already found the first derivative. I've already done the sketch of sign analysis for it. So I might as well use the first derivative test to find my max and mins because so much work is already done for me. Okay, so a little recap on the first derivative test. What you do is you use the sign analysis of your first derivative again. So I'm just going to recopy it because I'm going to write some stuff on it. So I'm just recopying the sign analysis I've already done. I have to use it again. This time I'm just using it for something different. So -1, bounce, 1. Okay, so if you recall, the way we figure out max and mins using the first derivative test is looking at where I switch from positive to negative or negative to positive. So again, here I am positive, and then at that point right there, I switch to negative. So you may remember me drawing a little arrow to that point and writing switch or something like that. So whenever we switch from a positive to a negative, on the first derivative sketch, that is defined as a local max. So I know I'm going to have a local max at -1 on my true real graph. Okay. And then I have a switch right here again. I have a switch again. This time I am switching from negative to positive, right? So this is the opposite. I have a switch, but this time this will be a local min. So I know I will have a local min on my original graph at 1. There is no switch right here. Okay, I'm negative and I'm staying negative at that dot, right? So that's no switch. That's not going to give me any answers. Okay, so I know where they're going to be in terms of X, but it's always a point, right? A max and a min is always a coordinate. So I need to find my other half. I need to find my Y values. Okay, so just to save time, I've calculated those for you. I'll start with the max. So like I said, I know I have a local max at -1, but now I have to figure out my Y value. So what you do is you take that -1 and you plug it into the original function, f of x. Remember, we're trying to find stuff out about the original function. So even make a note in your notes here, plug into f of x. And when you do that, you would get 2. So just to save time, I'm just going to tell you that answer. Okay, same thing with local min. We've already established I have a local min at +1. And when you plug +1 into your original function, you would get -2. Okay, so there are your local max and local mins. We're getting there. Am I running out of space? I am. Okay, we have 2 steps left. Step number 7, I can do right here. And then step number 8, the graph I'll do right beside. Okay, so step number 7 is concavity and inflection points. So this is back to lesson 2. So in lesson 2, 3, I forget. We figured out concavity and inflection points. When is the graph concave up and concave down? And the way you figure out concavity is with the second derivative. Okay, so I need to find my second derivative. So my second derivative of f of x would be 60x cubed. And then I would minus 30x. Okay, beautiful. Once you find your second derivative, you need to set that equal to 0 also and get your x values out. So I'm going to factor out the GCF here of 30x, and I would have a 2, I'd have an x squared, I'd have a -1. Again, we have this monomial guy out here. He's going to give me an answer of 0. Okay. When I set this guy equal to 0 and solve, the 1 will get sent over. I will divide by 2. I'm going to square root each side. So you have 0.5 essentially, but you're going to square root 0.5 and you will get plus or minus. Don't forget plus or minus. And if you want to match Mr. P's solutions, he always goes to 3 decimal places. So I'm going to do the same thing here. Okay. So once we find these x values, we have to do sign analysis again. So now I am doing sign analysis on my second derivative. So it's going to look different. Okay. Again, I can visualize that. That is a degree 3 polynomial that's positive. And you can see here, I don't have any multiplicities of x squared. Yes, that's an x squared. Okay, but that's not what we look on. We would look at an exponent on the outside, and we don't have one on the outside. So all of our multiplicities are normal here. Okie doke. So I plug in my 3 values I found. I have negative 0.707. I've got my 0 in the middle, and I've got positive 0.707. Okay, degree 3 polynomials that are positive start down low, head up, crisscross, and end up. Okie doke. So again, we can look at where am I negative down there, positive, negative, positive. So my sign analysis is done. Okay, so my concavity, I would be, just to save space here, I'm going to go up here. So if I am concave down, I am going to be concave down wherever I'm negative. So negative infinity to negative. Oh, did I not put a negative in front of that value? Sorry. Negative 0.707 is my first value. So negative infinity to negative 0.707. And then with a union, again, I'm just trying to save space. So I'm going underneath 0 to 0.707. Okay, and then I would be concave up during my positive intervals, which is negative 0.707 to 0 with the union, and then 0.707 to infinity. Okay, also, number 7 asked us to find inflection points. Okay, and I did the work for you here again. I've plugged it in already. Oh, shoot, why did I just do that? Oh, undo, there we go. Inflection points occur there at those 3 locations, okay, whenever you switch. So I know I'm going to have an inflection point at those 3 locations. Again, that's only half the battle. I need to find my Y values also. So the first thing you do is you will start with your first X value, which is negative 0.707, and you will plug that guy into your original graph. Again, whenever you're plugging in to find a point, you're always plugging into your original. When I plug that gross negative decimal into my original polynomial, I get an answer of about 1.237. I repeat the process with 0, my next point there. When I plug 0 in, I'm going to get a result of 0. And finally, when I plug in my last value, 0.707, and I plug that into my original graph, I get negative 1.237. So you have 3 inflection points, 3 times that you're going to be switching from concave down to concave up. Okay, we are there, you guys. We are at the graphing point, okay? Now, these can be rough sketches in your notes. If you want to grab graph paper for your actual sketches, be my guest. I've got my x-axis, my y-axis. Okay, so I need to make sure that when I do my scales here, I hit all the numbers I need to hit. My x-intercepts and y-intercepts are not very high. 1.29 is the max. Okay. And then my local max and my local mins go all the way to 2 and negative 2. So I don't need to go very far in terms of my scales. So I'm going to go 4 on each side just to space it out a little bit. So I've got negative 4 to 4, and I'm going to do the same thing top and bottom. Actually, I'm just going to do 3. I only need to go up to 2, so. Okay, so there I am. Okie doke. So I actually have to go back and figure out what points do I actually draw. Not all of these are points, right? Like this right here, don't confuse that with a point. That is an interval. That's when I'm concave down. That is not an actual point to plot. The only points I have to plot are my X and Y intercepts and my local max and mins. Okay, and then my inflection points. Everything else is just telling me the behavior of the graph. So I'm going to start with my X-intercepts. I know that my graph crosses the X-axis at plus minus 1.29. So about there, there's my positive 1.29 and my negative 1.29. And then my Y-intercept, and I have an X-intercept at 0 as well. So that's a shared point. Okay, I have a local max at negative 1, 2. And then I have a local min at positive 1, negative 2. And those are actually the only points I have. Now, we also know behaviors of polynomial functions. We did them all in pre-calc 30, right? So we know that degree 5, an odd degree, and it's a positive degree 5, that my arrows are going to behave like that. So we can see now that I would go up, come down, hit my min, and go back up. Something like that, right? And what you can just do now is you can confirm that all of your other points are making sense. So what I mean by that is our inflection points. I should have an inflection point at around negative 0.707 and 1.237. So negative 0. I'm blanking here for a second. Negative 0.707. And yeah, so sorry, that's like right there. That's about my inflection point right there. So that's kind of when the graph, it's coming down and it switches at this point to be concave down to concave, sorry, concave up to concave down. And then at 0, 0, I'm going to be switching again. So it's kind of like this isn't a very good graph. I should probably redraw this. And I would just restart videotaping the whole thing again, but I'm already too deep, so I'm not going to do that. My graph isn't very good. The next one would be 0.7 and negative 1.2, so about there. So as long as the points that you found are on the graph, like if you found an inflection point that's way up there, obviously something went wrong. But my 3 inflection points I found, I can locate them on the graph. Okay, so I know I'm doing it right. And if we actually graph this properly, like if we went to Desmos or something, we would see the concavity making a bit more sense. I just didn't draw this very well. My line here should be more like that, kind of concave in a little bit. So just know that I will be lenient in terms of whether your graph is kind of bowing out or going more straight. I'm okay with that, especially because I clearly just didn't do it well myself. That's my apologies. But I know that my graph is right in terms of all of my points. Okay, all of my inflection points I got hit. I hit my x-intercepts, I hit my y-intercept, I hit my max, and I hit my min. Okay, so I know I'm good. If you want to confirm you're increasing and decreasing, you know that you should be increasing from negative infinity to negative 1. Negative infinity to negative 1. I'm blanking again. What's going on? Negative infinity to negative 1. Increasing, but you're, oh, sorry. Oh my gosh. I'm negative 1 up here. Sorry. I was thinking I was negative 1 right there. I am not. Oh my God. You guys are so laughing at me right now when I'm not there. I know it. Okay. I am increasing all the way up to where x is negative 1. And then I am decreasing all the way down from negative 1 to 0, right? And I'm still decreasing from 0 to 1, and then I'm increasing from 1 to infinity. I did it right. I just wasn't thinking very clearly. Okay, so that's it. That's your graph. Everything is making sense. All the work we did is matching. Everything's jiving. So we are done. Okay. This is a long lesson, I know. I'm going to go quicker on this one to save time. And of course, you can always go back and listen to the video again. Okay, rational expressions. I have a fraction here, so I know this is going to be a little bit more complicated. Domain for sure is going to be a bit more complicated. Whenever you have a denominator, it's going to affect your domain because your denominator cannot be equal to 0, right? So before I state the domain officially, I am just going to take my denominator and I'm going to say that he cannot be equal to 0. I'm going to send x squared over, make it positive. I'm going to square root each side. So I know that x can't be equal to plus or minus 1. Okay, that's part of my domain. So when I list my domain, I say that x can be whatever it wants as long as it is not equal to plus or minus 1. Those are the only conditions. And we know by now, we've graphed enough rational expressions that those are going to be our vertical asymptotes. Wherever your denominator is 0 are your asymptotes. Okay. Step number 2, my x and y intercept. So for my x-intercepts, I'm going to set y equal to 0. So I have 0 equals x squared over 1 minus x squared. I'm going to multiply each side by my denominator. My left side remains 0. I only have x squared, and I just have a lone answer of x equals 0. So I know I have an x-intercept at 0, 0. Okay, y intercept, I'm going to set x equal to 0 this time. So I have y equaling 0 over 1 minus 0 squared. Well, that's 0 over 1, and that is 0. So again, I have a shared x and y intercept. They are both at 0, 0, the origin. Okie doke. Step number 3. Okay, this is that symmetry thing again. So I told you to figure out symmetry, you always start by figuring out what is f at negative x. So I have negative x squared all over 1 minus negative x squared. And we see how it affects our symbols. So if I square a negative, I'm going to have just a positive x squared. And then down here, I have 1, and then I have a minus. And then again, when I take negative x and square it, it's going to become positive x squared. So we can now take a look at our answer and we compare it to our original. When we compare it to our original, we see nothing changed. When it ends up being the exact same and nothing changes, that means we have even symmetry. Okay? So, even symmetry. And that means we are symmetrical about or around the y-axis only. Okay, so just a reminder up here, I forgot to mention that because I was dying when I was drawing this graph. We talked about odd symmetry here, and I said it would be symmetrical about the x and the y. Okay, so you'll see that it's essentially reflected vertically and then horizontally. So imagine folding this left side over onto the right. It wouldn't match up, right? You would have a max right there and it would go like that. But then we also flip it vertically. So that max is flipped upside down. So that's what it means to have odd symmetry. Even symmetry is it's only about the y-axis. And again, if I hopefully remember, I'll explain that once I'm actually graphing it. Okay, step number 4 are my asymptotes. So we've already established that I have vertical asymptotes at x equals plus or minus 1. Okay, but sometimes we have horizontal asymptotes with rational expressions. And the way we figure those out is we compare the degrees. Remember that? Numerator and denominator. Compare the biggest degree. So my numerator, so this is my horizontal asymptote work. Okay. My numerator is x squared, and my highest degree on my denominator is negative x squared. So you take both terms. So I have an x squared and a negative x squared. And when it's a tie, which it is, when it's a tie, you just compare the coefficients or find the ratio of them. So 1 over negative 1 is negative 1. So I have a horizontal asymptote at y equals negative 1. All right, so I've got quite a few asymptotes. Okie doke. Step number 5. This is where I get into the stuff we've been learning this semester. So step number 5 is your increase and decrease. So to do that, I need to find my first derivative. It's a fraction, so I need to do the quotient law. So the derivative of my numerator is 2x. I multiply that by my denominator unchanged. I subtract the derivative of my denominator, which is negative 2x, and I multiply that by my numerator unchanged, and I divide that all by my denominator squared. Okay, we're going to have to simplify because we had to do sign analysis on this, right? So we have to clean this up. Okay, so I'm going to distribute that guy in. I have 2x minus 2x cubed, and then these will become 2x cubed, and those will make it a positive. So positive 2x cubed, and that is over 1 minus x squared squared, and I can see that that and that are going to cancel. So my final simplified answer is 2x over 1 minus x squared squared. Okay, we got to do sign analysis on this guy. And unfortunately, it's hard for us to visualize these guys. So when you do sign analysis on these, I recommend doing that table of values, right? So first, I need to figure out what my critical numbers are to plot. When you have a fraction, remember that your denominator will give you critical numbers also, right? So my function here is undefined when x is equal to plus or minus 1. So I know for sure I'm going to have critical numbers of negative 1 and 1. And then if you want to see if there's any other critical numbers, you sub him in for 0, and you would multiply each side by that, which we know just results in the left side still remaining 0 and your denominator disappearing. So I would have 0 equals 2x divided by 2. You have one more critical number at 0. Okay, so if you want to write in your notes, x is undefined at plus or minus 1. So we know those are critical numbers also. We learned that back in lesson 1. Okie doke. So what you want to do for tables of values is you want to pick some numbers in each chunk. So right in this chunk right there, I'm going to pick negative 2. Next chunk, unfortunately, we have to pick negative 0.5. Next chunk, positive 0.5, and the final chunk is 2. And remember, 0.5 is gross, but really we're only concerned about our symbols, right? So I have to plug negative 2 into this and see what would happen symbolically. Look at your denominator. No matter what we plug in those brackets, whether the brackets become negative or positive, we are squaring it. So we know my denominator will always be positive. So all I got to do is figure out my numerator. So if I plug in negative 2 up top, that becomes negative 4. So I know I'm going to have a negative over a positive. It's going to give me a negative. There's my sign analysis done for that chunk. If I plug in a negative up top, it's going to give me a negative again. Negative over positive, negative. Okay, if I plug in a positive 0.5 up top with the 2, it's going to result in a positive. A positive over a positive is positive, and it would be the same for that guy. Okay, so my increasing interval is whenever it is positive. So my increasing interval is from 0 to 1 and 1 to infinity. And my decreasing is whenever it's negative. So negative infinity to negative 1 with a union of negative 1 to 0. Okie dokie, done. Now we go on to step 6. Step 6 is where I figure out my local max and mins. So again, we can figure out our local max and mins with the first derivative. So I'm going to rely on all of the work I did from step 5 and just use it again. So if I look at step 5, and to save space and time here, I'm not going to recopy the sign analysis like I did in the first example. I'm just going to say, look at number 5's sign analysis. Okay, we will have a max and a min wherever it switches, right? So the only time I switch symbols from a negative to a positive is right there. That's the only time I go from a negative to a positive. When I go from a negative to a positive, that is defined as a local minimum. So I know I'm going to have a local min when x is 0. And remember, that's only half the battle. You have to find y now. So you take that 0 and you plug it into the original function. When I plug 0 into the original function, I get 0 over 1, which is just 0, which is that point right there is also my x and y intercept. So I've got another shared point there. Okay, that was quick. All right, step number 7 I'll do right here. That is my concavity. Now this one takes a little while, especially because to find concavity, we need to find the second derivative. So I'm going to do my second derivative, and I'm going to use this guy right here, right? That is my first derivative simplified. So I'm going to use that. So derivative of my numerator is 2. Multiply that by your denominator, which is 1 minus x squared squared. Then I minus off my derivative of my denominator, which I'm going to have to use the chain rule. I've got to drop that 2 down in front, recopy my bracket, and then chain rule says I have to find the derivative of that. Okay, and then don't forget you have to also multiply that by your numerator unchanged. Gross. And then you have 1 minus x squared. It was already squared, so when I square it again, that's actually going to be a 4. Okay, this looks disgusting. Now, what I want you to look for are any common factors you have. You see how you have a 1 minus x squared everywhere? You have 2 of them here, 1 of them there, and 4 of them here. You have a common factor essentially in all of your terms. So let's slash. There'd only be 1 left here, none left there, and only 3 left here. And I'm going to kind of simplify as I go as well. Okay, so I have this 2, and I know I have one of these brackets left. So I'm going to distribute that 2 in. I would have 2 minus 2x squared. Okay, here, this bracket is entirely gone, so I have no distributing to do. I just need to kind of combine these 3 guys. 2 negatives would make a positive, so I know I have a positive for sure. And then 2 times 2x is going to be 8x squared. And then that is all divided by my denominator cubed now. Okay, and the last thing I can do to simplify is I can combine my x squared. So I have 6x squared plus 2 on top, 1 minus x squared cubed. Okay, I need to now do sign analysis on this guy. So be able to do that, I need to find what my C values are. So again, when I plug 0 in to where my f double prime of x is, I'm going to have 6x squared plus 2. Now, I'm just going to skip a step here. Don't write this down. I would normally have my denominator down here, but then I would multiply it on each side to cancel it out, right? I know my left side will remain 0, and I know it'll just disappear on the right side. So that's really what I'm at. Now, if I try to solve for this, say you factor, say you move the 2 to the other side and it becomes negative. Regardless, at the end, you would be trying to square root a negative, right? When that 2 gets sent over, it's a negative 2. When you divide by 6, it's negative 2 over 6 or negative 1 over 3. When you go to square root a negative, you can't. So this cannot give you any critical values, okay? There's no value for x here that we can pull out. However, don't forget that your denominator can still give you critical values as well. So just like my sign analysis over here, my denominator, 1 minus x squared cubed, that can't be 0. Even if you cube root each side, you're still going to have 1 minus x squared can't be 0. So again, x can't be plus or minus 1. That's kind of your restriction, right? And those restrictions are critical values also. So when I do my sign analysis, those are my only two values I have, -1 and 1. Okay, again, I can't visualize this. I have to try to do sign analysis on this guy. That's my simplified guy, and I can't. So I am going to, or I can't visualize it, I should say. So I'm going to do my table of values. I need to pick a value in my first chunk, which I'm going to pick as -2. Then I'm going to do 0 in the middle and then 2 on the right. Okay, when I plug -2 in here, that's going to square. It's going to become positive. No matter what you plug in for x up top, once you square it, times it by 6, then add 2, your numerator is always going to be positive. So when you're doing this test, always try to look for those little tricks. My numerator is going to be positive no matter what. I'm only focusing on my denominator. Now, when I plug my denominator in, it's always going to end up being a positive. But because I'm going 1 minus, I got to figure out if that results in a positive or negative. So when I plug in -2, square it, that's +4. 1 minus 4 is -3. A negative cubed will remain negative. So positive always on top, negative on the bottom, that'll be negative. Okay, 0 on the bottom, 1 minus 0 is 1. 1 cubed is 1, that's positive. So here I have a positive over a positive, that's positive. And whenever I plug in 2, it's going to be the exact same scenario as that guy. Okay, so 1 minus 4, it's negative. When I cube the negative, it's still negative. So negative over a positive. Okay, so negative, positive, negative. There we go. And this tells me my concavity. Sorry, guys. I know I'm running out of room here. Hopefully you wrote a bit smaller than me. Okay, so concave down is whenever I'm negative. I am negative from -infinity to -1 with a union of 1 to infinity. And then I'm only concave up from -1 to 1. And then my inflection points is where we can cheat a little bit. We have no work because inflection points, pardon me, inflection points, oh, I'm just going to draw this in, sorry. I just wanted to draw this in. So you know that in theory, these are asymptotes, right? Okay. Okay, so the reason we have no inflection points is because of these asymptotes, right? So remember, an asymptote is where the graph doesn't exist. So the graph actually doesn't exist here. So inflection points are wherever we switch from concave up to concave down. So that we'd be tempted to say we are switching here because we're going from a negative to a positive. But we can't be switching there because the graph doesn't exist there. We can't have a point there, even if we wanted to. Same thing here. You might be tempted to say we are going from a positive to a negative when we're switching concave up to concave down. So that would be an inflection point, but it can't be a point on the graph because we know there's an asymptote on the graph there. I hope I'm making sense. So that's why I wanted to draw those in all of a sudden, just to see that visual. So there are no inflection points. Okay. Oh my goodness, we're almost there. All right, step 8, let's graph this bad boy. Now, believe it or not, we did all of this work, all of these steps, and we actually only found one point. If we go back and we look at our x-intercept, our y-intercept, and our local min, those are the only actual points we found, and they're the same. We've only found one point. Okay, so we're going to have to rely on the other stuff to make sure we graphed it right. I do know I have asymptotes though, so I can draw those in. Okay, I'm going to go to 4. And then I'll go to 3 again. So again, the only point I have is 0, 0. Okay, so there's the only point I know for sure is there. I do know that I have a vertical asymptote. That's my vertical asymptote at x equals 1. And then I do know I have a vertical asymptote at x equals -1. And then I also know that I have a horizontal asymptote at -1. Don't forget about that guy. That's at y equals -1. Okay, now we have to rely on our knowledge from Pre-Calc 30 and rational expressions. In Pre-Calc 30, we learned that rational expressions were essentially made up of curves, okay? Little U-shapes, parabolas, that type of thing. Now, when I taught Pre-Calc 30, I always taught my kids to look at how many sections you've created with your asymptotes. We've essentially created 6 sections, okay? 1, 2, 3, 4, the corners, and then the 2 in the middle, 6 sections, okay? We also know that I'm going to be symmetric about the y-axis. So whatever happens on the left will happen on the right, okay? So what we're going to do is we're going to look at some of our intervals, okay? For example, I know that I am decreasing from -infinity to -1. That's over here on the very left, right? And then I know I am also decreasing from -1 to 0, and that's this portion right there. Okay, so I am not going to draw it yet. I'm just going to explain a bit more. Okay, then I'm also decreasing from -1. Sorry, I said that one. I'm increasing from 0 to 1. That's that right there. Okay, so with those two pieces of information, I just said that I am decreasing from -1 to 0. So that's that. And I know I have to cross that point. And then it tells me that from 0 to 1 right here that I'm increasing. Okay, so my increasing and decreasing intervals, specifically this one and that one, kind of tell me that I have a parabola. Okay, I'm decreasing, I hit my origin, and then I go back up and I'm increasing. Now, whenever we have rational expressions, if you have a parabola in the upper quadrant, your other curves are going to be down low. Like they're not going to be up here beside. Okay, they're going to be underneath your asymptote. So because I know that they're underneath my asymptote and that I have to be decreasing from -infinity to -1, that has to be this section right here. So there's my U-shape there. And then I know I am symmetrical about the y-axis. Okay. I also know I'm increasing from 1 to infinity. So increasing looks like that. I'm going up. And I have to be symmetrical. So it's going to be the same on either side. So I've got my curve on the left symmetrical with my curve on the right. I'm also symmetrical here. My left is symmetrical with my right. And that is how specific you need to be for the graph. It's kind of a lazy graph, but we've used our information. Again, we can look at concave down and up also. Am I concave down from -infinity to -1? Well, that's this guy right there. Yep, that looks concave down to me for sure. And then am I also concave down from 1 to infinity? Yep, I am concave down over there as well. And then I am concave up from -1, and I'm concave up also from 0 to 1. And then I have no inflection points because I have no switching. We already talked about that. So I know that was so long. Oh my goodness. I'm so sorry. Tomorrow's lesson is shorter, much shorter. So you will have time tomorrow to work on this. And then you also have a work period on Thursday. Okay, I'm so sorry that that was so long and that I lost my brain on question number 1. I am in the building today, so I'm going to pop down and see you guys if I can. Okay, bye.